All right, so what a matrix is basically an arrangement of information in a rectangular tabular form. That's all a matrix is. It's just a way for us to organize and arrange information in a rectangular array. Okay? Whoops. So it's a rectangular array of variables or constants in rows and in columns. That's how it's organized. And each value is called an element. So each specific entry is called an element. We used to have the word entry more frequently. Now, I guess element is taking over. All right, so here's how we arrange a matrix. So the dimensions or the size of the matrix is the number of rows and the number of columns. We always talk about the rows first. So how many rows it has? It's got m rows and n columns. And the dimensions is given by m by n. Okay, mxn, m by n. Now, if we go inside the matrix here, how many rows and how many columns does this have? It's got 1, 2, 3 rows, and it's got 1, 2, 3, 4 columns. So the dimensions of this are 3 rows by 4 columns, 3 by 4. So we just say, okay, given a 3 by 4 matrix, etc. Now, let's talk about some of the elements. If you look at this element, -1, where is this located? It's located in the second row. Always, the row always comes first. Second row, first column. So I say this is A, 2, 1. Second row, first column. Now what about the variable? If A is the name of the matrix, name always gets capital letters. The name of the matrix always gets a capital letter. So if the name of this matrix is A, capital A, then each entry then is little a. Okay? So this one, in the place of the second row, first column, is little a, 2, 1. This one here is in the third column, the third row, second column. So it's A, 3, 2. Row 3, column 2. Okay, so that's just how we organize the information there. All right, let's do an example. Here we have a rather large matrix. We're not really going to be working too much with matrices of this size. It says to state the dimensions of A. So it's got how many rows? 4 rows by 1, 2, 3, 6 columns. So it's a 4 by 6. And if you say 6 by 4, then it's just wrong. There is no partial credit, it's just wrong. Okay? Yes?
Are we using a calculator to, like putting in
very small amounts. Right.
That's not what we're supposed to do.
No. Okay? There are very specific things for which you're going to use your calculator. There is a lot that you will have to do without a calculator. The matrix is used to organize information. So for example, and we're going to do some examples like that. So for example, if this was, if you had, for example, a store where you sold different items and they each had, different prices. So you would say, okay, item number 1, I like a computer, a CD, or whatever. And here, they're the prices, right? And you could put in like how many of each at each price was sold. Okay. All right, so here it says find the value of the following elements. So the element A, 2, 3. So this is second row, third column. It's what? 0. Okay, A, 3, 5. Third row, fifth column. That's a 5. A, 4, 6. Fourth row, sixth column. 11. And if the dimensions are 4, 6, and you want the entry at 4, 6, that's just going to be the last one, right? And A, 1, 2, that's the first row, second column, -3. Okay. No. It's two different entities.
So the numbers go by like 1, 2, 3,
Yes.
4, not 1, 2, 3, 4.
Yes, you start at the top left, okay,
Okay.
and you go down and to the right. Okay. Now, sometimes you have matrices with special names. For example, a row matrix is just a matrix with one row, okay? So what are the dimensions of this matrix here? 1 by 4. You can have a column matrix where it's just one column. What are the dimensions of this matrix? 2 by 1. You can have a square matrix. Here's where you have the same number of rows and columns. In this case, this is a 2 by 2. We're going to be working a lot with 2 by 2s and 3 by 3s. You can have a zero matrix where each and every single entry is 0. Each and every single entry. And an identity matrix. The identity matrix has a very, very big significance in the world of matrices. What it is a matrix where every element in the diagonal is 1 and the rest are zeros. That's key. Okay? And the rest are zeros. Yes. Matrices are used a lot in the world of computer science. They're used a lot in solving for, like in chemistry, when you get, really detailed, and it becomes physics at that point, solving for like the states of the electrons, like the angular momentum, like the L, M, N, P, right? Those LMNs, they're all entries in a matrix, okay?
And do you have to label the zero matrix and the identity matrix as 2 by 3 and 3 by 3?
No,
So 3 by 3.
I don't need to do that. So this is the identity matrix. You should know what an identity matrix is. Okay, so this, the diagonal going from left to right is called the main diagonal. They're square, but they don't have to be 3 by 3.
Do they have to be square?
Yes or no. So you could have a row of zeros underneath, but basically the main diagonal must be a 1. Okay, so let's talk about matrix operations. When you talk about numbers, you are now very comfortable with what to do with numbers. You can add numbers, you can multiply, you can divide numbers. Matrices are not as, they're not exactly the same. Addition and subtraction is one thing, but then when it comes to multiplying matrices or dividing matrices, it's a whole other ballgame. Now, first of all, to add or subtract matrices, they can only be added or subtracted if they have the same dimensions. Not similar dimensions, the same dimensions. 2 by 3 and a 2 by 3. Okay? Otherwise, you can't even add them. You just say it's not possible to add them. When we add, so to add or subtract, all we have to do is add or subtract their corresponding elements. So for example, look at this case. You have an A matrix and a B matrix. This is the element 1, 1, right? First row, first column. You add it to first row, first column of the other matrix, and the answer goes in first row, first column of the resulting matrix. Okay? Similarly, this one is second row, first column. You add it to second row, first column, and in the answer space, it goes in second row, first column. Okay? All right, let's do a couple of examples, and it'll sink in. All right, so here we're adding A plus C. A has dimensions 2 by 2, C is 2 by 1, so it's just not possible. So you just say not possible. Not no solution, not possible. Okay. Here we're going to do B minus A. So let's write down our matrix B. Minus A equals. Now, what are the dimensions of the resulting matrix going to be? 2 by 2, okay? All right, so in the first spot, I have 10 minus 2, okay? In the second spot, I have negative 2 minus 5. Then I have negative 3 plus 1, right? Minus minus makes plus. Then I have 16 minus 3. Do you have to show that step? Not really. I'm just showing you now, all right? Obviously, you can do this in your mind. Yes? Okay, so this will help in partial credit, okay? 10 minus 2 is 8, negative 7, negative 2, 13. All right, so when it comes to things like this, there's very little complexity, so I expect that you just come up with the right answer. So there's also very little, fluidity as far as cutting you guys slack. So, just what do you call it? Fight for your points. Show me some work, okay? All right, so here we're done. Any questions? Okay. So this is a matrix. In science, sometimes you talk about vector quantities and scalar quantities. I don't know if you have yet. It comes up in physics, so maybe you haven't yet. A scalar in the world of physics is in the world of matrices, a scalar is just a basic number. Matrices are entities of their own. It's a collection of numbers, but it's an entity of its own, and it's very different from a scalar. So if you had, if there was a hierarchy, I would say, it was like matrices, and the numbers are like the little tiny plane people, okay? Now, scalar multiplication is multiplying a matrix by a constant, which we call a scalar. So regular numbers are called scalars. Scalar just means regular number. What you do here is each element is multiplied by the scalar, okay? So I'm just going to show the work here. You don't have to. You can do it mentally every time. Basically, you have to multiply each entry here by negative 3. So it's going to be negative 3 times 1, negative 3 times 0, negative 3 times negative 6, negative 3 times 5, negative 3 times negative 2, negative 3 times 4. And you get negative 3, 0, 18, negative 15, 6, and negative 12. All right? Please make sure that when you are writing a matrix, you put it in brackets. Sometimes people use, huge parentheses, but never just plain vertical bars, okay? So you can do, this. I don't like it, honestly. There isn't much difference. They mean the same thing. I like the brackets much better than that. The curly brackets, never. Never the curly bracket. Never the curly bracket, and never straight vertical bars. If you do straight vertical bars, it's actually wrong. That's what I mean. Never absolute value bars. Never. Okay?
What about the brackets?
The curly brackets,
Why can't you?
never. It's not an accepted.
I'm just wondering, so I know.
It's not an accepted symbol for matrices. That's set notation. Okay. So properties of matrix operations. So basically, when you're dealing with simple ordinary numbers, and when you add, addition is commutative. So 3 plus 5, 5 plus 3 are the same. It's the same in matrices. When you're adding, only adding, addition is commutative. Okay? So we have the commutative property of addition. Also the associative property of addition, meaning if you have to add 3 matrices to each other, A plus B plus C, you could add A plus B and then C, or you could add B plus C and then add A to it. It's the same. And then you have left scalar and right scalar, meaning if you're going to multiply by a scalar, you can either put it on the left side and distribute this way, or you can put it on the right side and distribute this way. It's exactly the same thing. I'm just saying that it also works for matrices, because there are some rules for multiplication, for example, that it doesn't work for matrices. Okay, so like when you're multiplying, 3 times 5 is 5 times 3 in numbers, but it's not that way for matrices. Okay?
Could you write like 2 A plus B and then 4, or would you just write A? Like,
oh, it's the same. It's the same. It's the same. You can. Yeah, it doesn't matter. Okay. So here we're going to do 3 times A minus B. So it's going to be 3 times. Okay, so you have A, 5 minus 2 minus 1, 0, 3, 2. And this is pretty much, you know, our order of operations. Minus B, 1, 0, negative 2, 3, negative 1, 6. Now look, when you after you subtract these matrices, you multiply it with the 3. Now, as a grouping symbol, I can put curly brackets outside, because these curly brackets are not for the matrix. They're just grouping symbols for algebra. Yes, you can, but it's more work. Yes, because the 3 must be distributed. Okay? I guess you can, like huge parentheses, you can do that. All right, so 5 minus 1 is 4. Negative 2 minus 0 is negative 2. Negative 1 plus 2 is 1. And here I have 0 minus 3 is negative 3. 3 plus 1 is 4. 2 minus 6 is negative 4. Okay? And now we're going to distribute the 3. So we're going to get 12 minus 6 and 3. Negative 9, 12, and negative 12. Okay? All right. So this is just basic operations. Often we use matrices in equations, and we have to solve matrix equations. Just like when you use variables in equations, 3x minus y equals 7, you can do that with matrices. In this case, the variable is a matrix, okay? Therefore, the solution will be a matrix as well, not just a simple scalar number, okay? So how do we solve a matrix equation? First, you're going to use algebra to solve the equation for x. Then, you're going to substitute the given matrices. So in this case, here is the equation that I have to solve. Okay? Now, you have capital X, capital A, capital B. Each of them, X, A, and B, are each a different matrix. Okay? So X, A, and B are matrices. So first, I'm just going to solve this like an algebraic equation. 2x minus a is equal to b. 2x is equal to a plus b. So x, this is a capital X by the way, is equal to half a plus b. Okay? So that's step 1. Step 2, I just put in my matrices. So for step 2, I say, okay, half times A plus B. This is half. The A matrix plus the B matrix, and you can use parentheses as a grouping symbol like this, okay? So what do we get here? Half times, if we add these, we get 4, 2, 0, 8, negative 4, 4.
You get minus 2 is minus 1 plus minus.
Oh, wait a minute.
For the 0, it's minus 1.
Okay, hang on. All right, hang on. So it's 4, 2, minus 2.
Minus 4.
So finally, we get 2, 1, minus 1, 4, negative 2, and 5. Okay? All right, so this homework will be due next time. Notice the page, it's P27. Okay? Okay, so previously you had solved systems of equations. Usually we have 2 equations and 2 unknowns, x and y. We also, though, solved 3 equations and 3 unknowns, and we used the same methods as we used for the 2 equations. Basically, it was either substitution or the elimination. Sometimes we call it linear combination, whatever. Now, so 2 equations and 2 unknowns represents 2 lines meeting each other at some point. 3 equations and 3 unknowns, x, y, z, represents 3 planes that meet each other. But it doesn't have to stop there. Just because we live in a 3-dimensional world, it doesn't have to stop there. You can have, 5 equations and 5 unknowns. You can have 8 equations and 8 unknowns. You could solve up to, like an infinite number. The point, the criterion is that however many variables you have, you need that many equations. So if you have 17 variables, you need 17 equations. Otherwise, you can't solve it. Now,
Yeah, that would be so much fun.
the elimination and the substitution are fine, but there are other methods, especially when the variables get, bigger in number, 4, 5, 6. In that case, we use matrices, and it makes things so easy, okay? So that's what we're going to do. That's what we're going to focus on in this chapter. We're going to talk about multivariable linear systems. Okay, X, Y, Z, maybe a W in there, all right? The first thing we're going to talk about is Gaussian elimination. So this guy, Gauss, Carl Friedrich Gauss, I believe, was a physicist. He worked a lot with magnetism. So like when you talk about magnetic fields, magnetic forces, he did a lot of work with magnetic fields. There is a unit for magnetism named after him. There are 2 units of magnetism. One is the Tesla, one is the Gauss, and I believe 1 Tesla is 4,000 Gauss, 1,000 Gauss, I believe. So it's like you could have 4,000 Gauss or 4 Tesla. Okay?
Is it Tesla or Teslas?
4 Tesla.
4 Teslas.
Either way.
The car is named after?
The car is named after that guy.
Didn't he
Tesla.
get sued for copyright?
He's been dead forever.
Okay.
Yeah, Tesla. The solenoid. The solenoid.
And the electricity. That's so cool.
The what?
He invented like a gun, electricity gun.
This is what he worked with. He worked with like coil. When we have a system of linear equations, we can use substitution or elimination, okay? And we can convert the system into triangular form, or a synonym is row echelon form, okay? What is row echelon form? Basically, it looks like this, okay, where you have a triangle. In the second row, the X element disappears. In the third row, the X and the Y elements disappear. All right, so basically you have a triangle and the bottom triangle just goes away. This process of converting the system of equations into triangular form is called Gaussian elimination. So when you do Gaussian elimination, you convert to row echelon form. On the test or quiz, I will just say, put the system or the matrix in row echelon form. You will know what that means. You will not ask what that means. Okay? This is what it means. Okay. So basically what you have to do is you have to eliminate all terms in the bottom left-hand corner. Okay? Okay, so here's how. There are a couple of operations you're allowed to do, and they're free. There are some things in the world of this matrices and all sorts. There are a couple of operations that you're not allowed to do. Absolutely not. There are some things that you do, but you sort of have to pay a price for it. Okay? So here are the things you can do, and they're free. You can interchange any two equations. So for example, you have equation 1, 2, 3. You can rearrange them. You can say, yeah, you know what, I'm going to write the bottom one at the top. I'm just going to rearrange the order. You can do that. You can multiply one of the equations by a non-zero number. So you can take equation 1 and multiply the whole thing by 5. Or you can divide the whole thing by 2. You can do that. It's just an equation.
Can you multiply more than one or just one?
No, you can multiply any one with any number. You can also add a multiple of one equation to another. Okay? You can add, so for example, you can add equation 2 and equation 3. All right? It's like elimination. So before, when we had, for example, 2x plus 5y equals 7, 3x minus 8y equals 2, and if you wanted to eliminate the x, what did we do? We multiply this by 3, we multiply this by -2, and we add them. So we're adding multiples of one equation to another equation. Okay? All right. So here are my little tips and tricks. First off, this one is a repeat. We don't need it. Okay? So first, you have to make sure the leading coefficient of x in equation 1 is 1. Okay? Then, you eliminate the x term in equation 2. You eliminate the x term in equation 3. You eliminate the y term in equation 3. And then you make sure all your coefficients are 1. Okay?